Okay, so we did the C matrix, and you can see that extracting information from the C matrix requires you to take square roots, cosine inverse and all this stuff in order to get shape change. But if the deformation is small, like what happens for almost rigid bodies, then there is a much more direct interpretation possible in a very nice way. So when H is full of small numbers, mostly less than 0.1, actually, usually for metals, it will be much, much smaller. It will be less than 0.01 or 0.001. Many times the displacement gradient will be very small. Then the diagonal terms can be used to approximate the stretch or the strain, and the off diagonal terms will tell you something about the rotations. This is very, very simple. So off we go. So let us take a look. Okay. When the displacement gradient is small, the terms can be easily interpreted. Let's see what I mean. So here's my small displacement. Now notice that every number there is 0.1 or less. Can you see first row is 0.1, 0.006, 0.06, 0.1. Second row is minus 0.1, minus 0.02, 0.05. Last row is minus 0.02, 0, 0.07. So all of them are quite a bit small. So what we mean is that every entry of H must be small. Then we can do some interpretation. So we want to explain the meaning of every term here. So here's my ith axis and jth axis. So for example, it could be xy or yz or xz. Here is my original line element of length dxi. So dxi could be dx1, which is dx, dx2, which is dy, and so on. That's my final shape. Can you see? That's my deformed shape. And you can see it's fairly close to the original because it's small deformation. The red arrow tells me how much it has moved. Okay. So the bottom, the diagonal terms approximate the change in length. That hii dxi, the diagonal term in h tells me how much is the change in length. Right? Original length is dxi. The change in length is hii dxi. You can see that in the picture. It's not exact. Can you see? Because the line is slant, but we are ignoring the height so that we're not using Pythagoras theorem. If you do Pythagoras theorem, then we are back to the old one about C. Here we are making an approximation that hii dxi is good enough. So that hii is delta li over li. So that is the ratio. Okay. So to be very specific, h11 equal to 0.1 means that the line element x1, which is the line element along the x-axis, becomes approximately 10% longer. H2 equal to minus 0.02 means that the y line element becomes approximately 2% shorter. Can you see negative sign means shorter? H3 0.07 means that the z line element becomes approximately 7% longer. Okay. The off diagonal terms, now you have to be careful. HJI, notice it's a reverse, approximates the angle that light element along the I-axis rotates towards the J-axis. Right? How much does the line elements rotate? So for small angles, you can see that in the figure that tan phi ij is rise over run, which is HJI dxi, that is the rise. The run is approximated as dxi. Can you see that we are not putting that 1 plus hij? So you can cancel it and you'll get hij is the tan phi, and which is approximately phi because it's small deformation. To interpret this, we go column by column. So we look at the first column of H and we say that the off diagonal terms in the first column of H mean the following. The x line elements rotates 0.1 radians away from the y-axis because H21 is minus 0.1, and 0.2 radians, 0.2 radians away from the z-axis because H31 is minus 0.02. Can you see the first column of H? That's what is happening. Okay. Similarly, the y element rotates 0.6 radians towards the x-axis because H12 is 0.06. Sorry. And 0 radians towards the z-axis because H32 is 0. The z-line elements rotates 0.1 radians towards the x-axis and 0.07 radians, sorry, 0.05 radians towards the y-axis. Can you see? So you can go column by column and read off what happens to each of them. So every rotation, every strain can be directly read off from H. That's the idea.